it's a really useful tool. Okay, and it's interesting because it operates on binaries. Okay, it doesn't really do things on source code. It operates on binaries, and that makes it very convenient, because what it does is that you compile your program, you're ready to run the binary, and then something goes wrong, you can debug that using Valgrind. So Valgrind is used for primarily two things. It can do many other things. Primarily it is used for these types of use after free and spatial errors and things like that. It is also used to track down. What is the second thing it's used to track down? Memory leaks. Yeah, memory leaks. Yeah, that is true. You do use it for memory leaks. I almost forget. What is the other thing that it does well? Yeah.
Invalid memory access.
Yeah, that's what I said now, right? So, but I don't know exactly what you mean by invalid memory access.
Out of the bounds of an array.
Right. So that's what I talked about, right? So use after free can detect. It can not. I'm not sure whether it always detects. It can. Yeah, it can detect all of those. It can definitely detect out of bounds access. But there is another feature that it has, which often turns out to be more useful for bug tracking than the memory stuff. No? A lot of people raised hands that they used Valgrind. Uninitialized memory access, right? So that's something that is the most common bug that it identifies, and it is extremely useful. Yeah.
Why didn't you classify that as memory stuff?
It's not memory error per se, right? Because memory error is something about accessing, right? So we defined what memory errors are, right? We said spatial error and temporal error, right? Neither of those have anything to do with uninitialized memory access, right? So therefore, it's not a memory error, because we define memory errors as a problem relating to pointers and not a problem relating to the content of the objects. Yeah.
Wouldn't temporal errors be kind of related to uninitialized access of memory?
Kind of, but I don't want to talk about that, because I have a feeling that talking about it will end up causing more confusion than clarity.
Sure.
So if you want, you
Yeah.
can talk to me later on. Okay, so that's one class, and so then there is a second class of techniques which basically check pointers, and then especially they check pointer arithmetic, right? So these techniques maintain metadata associated with pointers, right? So here, what we are doing was we are putting something around the object, right? So the pointers themselves didn't have anything, right? There was information around the object, and the pointers were somehow, used to check whether they were. So here, the information is associated with the pointers, and so basically there is, think of maintaining some kind of a lookup table that says, here is the legal bounds for every pointer, okay? And so whenever a pointer arithmetic is done, it checks whether the bounds of the resulting pointer and the bounds of the original pointer are the same, right? Are they pointing to the same object, or are you starting with one object and then you perform some arithmetic, you end up going to something that's outside the bounds of the original object, right? So in order to do this, what needs to be done is you need to maintain this table, that says here are the valid objects, and so and then each pointer arithmetic is first going to look up this table to find out, okay, what object do I belong, okay, and then it returns that, and then after the arithmetic I again ask what object do I belong, and if the two are same, I'm done. If not, there's going to be an error that's printed. So this technique leads to some problems because sometimes you perform pointer arithmetic but you don't access the result. Okay, so and you can imagine that what's wrong with, you know, setting, let's say you have an index variable, right? So you're going to access a sub I, right? So think of somebody announcing an error as soon as you set I to a value outside the array, right? So something like that, because you can see that, okay, setting I to a value outside the array is not itself wrong. Only if you do a sub I after doing that, then it is wrong. Okay? But this one eagerly, you know, announces an error as soon as you set the pointer to outside the object. So it leads to some compatibility problems, and people have tried to make it better, but in the end, it's not a complete, a fully satisfactory solution. Okay, so you still have some potential problems. It's not that it's hard to avoid these problems. So if you write, you know, a new program, it's very easy to make sure that it doesn't get flagged by this technique, right? But again, as I said, there's tons of code that was written long ago, and you know, compile it, and you run it, and it gives you this error. Most people don't know how to, you know, track it down and fix it, or definitely they don't have the time to do it. Yeah.
I do not understand why accessing A of I after the bound is a problem that it is raising a flag. It is good that it should raise a flag, right?
No, it's just, see, the thing is that all you're doing is, so the problem is that it happens often in your program that you will go outside the bound. Okay? Because think of a for loop, right? When you terminate in the for loop, the ending value of I will always be one outside the array, right? So it does happen in real programs that you set the pointer to, you know, one element outside or things like that, and that itself is not a problem. Only if you dereference the pointer at that point, then it's a problem. Right? Clearly there's an error if you dereference a pointer that's out of the bounds. But if you simply set a pointer to point to something, that doesn't seem like an error that should cause the program to abort. Okay? And
So this seems more like a programmer's error. That if we have
but again, as I said,
bound-
programmer is always right? Because the programmer has been writing code for 30 years, and nobody can sit down and rewrite any of this code. Right? And that's why we have the problem, right? Otherwise, we would just say, you C programmers, you stink. Go away. I'm going to rewrite everything. Right? So then the third set of techniques are looking at maintaining even more runtime metadata so that they can do two things. So one of them is that they can not only detect spatial errors but also temporal errors. The second is to deal with this problem of invalid pointer that is never dereferenced. Okay? So this set of techniques, you can do anything with your pointers as you want, and it's not going to complain. But if you use an out-of-bounds pointer to dereference, then it's going to complain at that point. Okay, so it's a little bit, it's going to complain a little bit later, and because it complains a little bit later, you know for sure that when this technique complains, you know, you have a problem. Okay, this one, you may have a problem, and clearly if it is, you are writing code, it's better to avoid the problems that this first technique tells you. But if you already have, you know, a huge base of existing code, then you would rather prefer the sort of delayed error approach. So there are various techniques for doing this, and I'm going to just very quickly give you some idea of how this works. Okay. So the metadata maintaining, so in order to do this, what happens is that for each pointer, you have to maintain some associated metadata. Okay. So in this case, I'm going to talk about it as, so there's a pointer P, and you can call it, let's say the metadata as P info. Okay. And for dealing with spatial errors, you need to have two pieces of metadata, one that says what is the base of the object, and another one that says the size of the object. Okay. And then if you do P equals malloc 8, then thing gets allocated, okay, and then the base and size will get initialized this way. So the base will point to the base of the block, the size will be 8, right? And later on, if you do P equal to P plus 2, then the pointer will point advance, but notice that the metadata doesn't change, right? Because the metadata is about allocations. So the metadata gets set at the time of allocation, it never changes after that. Okay. So now, if you do star P, then it's going to check that the P value is between the base and the base to a size. So, and if it is, then you're okay. So it's like a subscript check, right? So it's going to do this check if P is greater than the base and less than the size, right? So then it's okay. Then P equal to P plus 14, then it's pointing over there, and then the check will fail because it's not between the base and size. Okay. Now I don't know whether there is another example. No, there's no example. But if let's say you have a Q equals P, so if you have a Q equals P, then immediately you'll have to also set, right? So meaning that every time you copy a pointer, you also have to copy the metadata associated. So this is how you do this third technique. Intuitively it's very easy to understand how it works. A compiler can, add this kind of instrumentation into your program, and then, all the memory errors will be checked. But you can see that there is obviously a cost, because for each pointer you have to, have some allocate memory for holding the metadata, right? So there is a memory cost. And then each time you do a pointer dereferencing, you have to do all these checks. And you can imagine that, okay, just one quick comment. So when the first computer I built, right, had a 1 megahertz clock, right? So and the memory that I was using had something in the range of few hundred nanoseconds access time. Okay, and fast forward to now, right? So we have processors that are like 5,000 times faster. The memory is maybe 2 or 3 times faster, right? Not that much faster at all. Okay, and so as a result, on a modern processor and a typical workload, memory accesses are the ones that determine most of the performance. Right? So the CPUs have become more and more powerful with multiple arithmetic units and whatnot, but memory has still remained rather slow. Okay? And as such, something like this, which causes a single memory access to become 3 memory accesses, is actually very expensive. And so these techniques end up having quite a high overhead. Often, there are many CPU intensive programs end up running 3 times slower, right? And then you can imagine that 3 times slower is just no way to convince anybody to deploy this type of technique. So now temporal errors requires even more data, because with what we did here, right? If let's say you said, and then let's say you did right? If you freed Q at this point, right? The compiler can figure out at this point, okay, if I free Q, I can go ahead and modify Q info so that that can record the fact that there is, Q is no longer pointing to any valid object. But the compiler cannot figure out that P also happens to point to the same memory location, and so it cannot update P info, right? And keep in mind that this assignment may happen in one function, and in another function that's far away, and this free Q may happen a long, long time after this is done, right? So there is really no easy way to figure out what are all the objects that could be pointing to the same place as Q. So there is no way to automatically go and update the metadata for all the things, and that's why the basic technique is not going to detect temporal errors. So the way you detect temporal errors is by adding even more metadata fields. Okay, so in this case, we are going to add something called a capability. Right. So this capability is going to help us figure out whether the reference that we have to an object is current or not. Okay. So the capabilities are stored in some place in memory, and every object ends up having a pointer to that capability store. So you heard this saying that there is not a single problem in computer science that can be solved with another level of indirection, right? So this is a case of that, because remember, what is the problem that we are trying to solve? We somehow want to make sure that when Q is freed, we have some way to mark everything like P, and maybe P came from some R, and R came from some T, and so on, right? All of those you want to make sure that those are all pointed, those are all marked as invalid, and we can do that by using this extra level of indirection, and let's see how exactly it works. Okay? So say malloc 8, and P gets pointed to that, and the base and size are set the same way as before, but in addition, this capability pointer is set this way, right? So this one, okay, this capability store says I am a capability for this particular place. Okay, and when you have a Q equals P, then again all the metadata is going to be copied. Okay, including so this part about simply copying P info to Q info remains exactly the same, right? You just have an additional metadata field. Now, star Q is going to be fine. Okay, so what it's going to check is that this capability store says it's valid. Now, free P. So now what's going to happen is that P is going to be whatever, right? It doesn't really matter what P is set to. But the more important thing is that, okay, so basically if you see what's going on, we are going to, when P is free, we are going to follow this pointer and mark this as invalid. So this way, anybody who is chatting that capability will know that it is invalid. So that's how, by using an extra level of interaction, we have solved the problem. if you do star Q, the capability check, fails. And there you go. Okay. So the way this is set up, you can see that essentially there's no way to reuse this capability, right? Because you cannot use this capability for some other memory object in the future because you never know who might be pointing to this, right? So that seems like a bad thing based on memory. So actually, you don't have to do that. Instead, you can sort of keep some kind of a sequence number here, and you can keep a sequence number here, and the validity check can be whether the sequence numbers match. Okay, and then every time you reuse this, you're going to increment the sequence count. Right? So this is if you think about it, you might understand how it works. If not, don't worry. The higher level bit is that it doesn't have to be that wasteful. You can reuse the capabilities. Okay, so that's
If I don't want to free the memory state, but I want to like get rid of the pointer,
yeah.
how exactly that is it?
You'll do p equal to null.
So that won't that make the capability pointer invalid as well?
No, only when you do free p. Only when the object is free, you're going to go and mess with the capability, right? When you just set the pointer to some value, that doesn't affect the target object at all, right? But of course, this is not a solution for memory leaks. So if you set p equal to null and q equal to null, you have lost all references to that particular object, so you have created a memory leak. But that's not the problem that this technique is trying to solve. Okay? So, okay, so let's, I thought we'll finish this pretty quickly, but I guess not. So we'll start the next topic and then we'll continue. Okay, so far we've been talking about buffer overflows and memory corruption and so on. So those aren't the only type of vulnerabilities. So what exactly are the other types of vulnerabilities that one should know about? Okay. So so especially with the increased use of web, there are a number of other types of vulnerabilities that still broadly fall under the topic of input validation errors. Right? That is, the problem still comes from the fact that there's a vulnerable program that gets input from some untrusted user who could be an attacker, right? And this program uses that input, and the way it uses this input, it could be tricked into doing something that the attacker wants. Okay, so that's so if the program was not vulnerable, it will check the input and make sure that the input cannot cause it to do anything that that is unintended by the program